Good morning, everyone, and welcome to today's presentation. I'm Dr. S.K. Singh, and I hold a PhD in this fascinating field. Today, we'll be exploring the basic theory of paper chromatography. Over the course of this presentation, I'll guide you through the fundamental concepts, how the technique works, and its applications. So, let's dive in and discover the science behind paper chromatography together. Today, I want to talk about the principle behind this separation technique. It's fundamentally based on the idea that the solute distributes itself between two different phases or solvents. We call these the mobile phase and the stationary phase. The mobile phase is typically the mixture of substances we're trying to separate, dissolved in a liquid or gas. On the other hand, the stationary phase is a porous solid matrix through which the sample in the mobile phase percolates. As the mobile phase moves through or over the stationary phase, the interaction between these two phases leads to the separation of different compounds in the mixture. These interactions are governed by various physico-chemical principles like adsorption, ion exchange, molecular sieving, and affinity. In essence, this technique involves passing a solution or suspension of a mixture through a medium. Because different components move at different rates depending on how they interact with the stationary phase, we can effectively separate complex mixtures. This principle underlies many of the powerful separation methods we use in analytical chemistry. Now, let's take a closer look at the classification of chromatography. Essentially, it is based on the interactions between the sample components and the stationary phase. These interactions help us differentiate the various types of chromatography. For example, we have partition chromatography, where the separation occurs based on partitioning between two phases. Then, there's adsorption chromatography, which involves the sample adsorbing onto the stationary phase. Ion exchange chromatography relies on the exchange of ions between the sample and the stationary phase. Gel filtration separates based on size, with larger molecules eluting first. Affinity chromatography is highly specific, utilizing biological interactions. And finally, high-performance liquid chromatography, or HPLC, offers high resolution and speed for separating complex mixtures. Moving on, chromatography can also be classified based on the nature of the stationary or mobile phases. We generally have two main types, planar and column chromatography. Planar chromatography involves a stationary phase that is present as or on a plane. Think of paper or thin layer chromatography plates. It's a simple, flat setup. On the other hand, column chromatography involves a stationary bed inside a tube, which can be either gas or liquid. This setup allows for continuous flow and is often used for larger-scale separations. To clarify, planar chromatography is a technique where the stationary phase is spread out on a flat surface, making it easy to analyze multiple samples simultaneously. Conversely, column chromatography involves passing the mobile phase through a column packed with stationary phase, which provides a more efficient and scalable separation process. Both methods are fundamental in our toolkit, and choosing between them depends on the specific needs of the analysis. Let's take a closer look at chromatography classification. As you can see, chromatography is a broad technique, and it can be categorized in various ways based on how the separation occurs. The main classifications include paper chromatography, thin layer chromatography, gas chromatography, and liquid chromatography. Each of these methods has unique features suited for different types of samples and analysis goals. For instance, paper and thin layer chromatography are often used for quick, qualitative analysis in labs or educational settings. Gas chromatography is ideal for volatile compounds, while liquid chromatography, including HPLC, is versatile and used extensively for complex mixtures. Understanding these classifications helps us choose the right method for our specific analytical needs. The core idea here is that chromatography is adaptable, and its different forms allow us to separate and analyze a wide range of substances effectively. This classification is fundamental because it connects to the overall theme of choosing the appropriate technique based on the sample and the information we seek. This slide focuses on how chromatography is used to separate mixtures of amino acids and peptides. Essentially, the molecules in a mixture get divided between two phases, the stationary phase, and the mobile phase, based on how much they prefer one phase over the other. The key idea here is that each molecule's affinity for these phases determines where it ends up during the separation process. We can perform chromatography in a couple of main ways. One is paper chromatography, and the other is thin-layer chromatography. Both methods rely on this principle of partitioning, where the separation occurs because different molecules distribute themselves differently between the two phases. Specifically, in partition chromatography, the separation happens because the components of your sample partition or split between two liquid phases. The stationary phase is usually coated with a liquid that isn't miscible with the mobile phase, which is another liquid moving through or over the stationary phase. A crucial concept here is the distribution coefficient, often called CADE. This coefficient describes how a compound, or analyte, distributes itself between these two immiscible phases. It's a constant value at a given temperature, and it's fundamental because it tells us how a particular molecule will behave during the separation process. In mathematical terms, the distribution coefficient relates to the ratio of the analyte's concentration in one phase to its concentration in the other. This constant helps us understand and predict how well a molecule will separate from others based on its affinity for each phase. So overall, the effectiveness of chromatography hinges on these principles: how molecules partition between phases and how their distribution coefficients influence their movement. And this understanding allows us to separate complex mixtures like amino acids and peptides efficiently. In this technique, separation is based on differences in adsorption at the surface of the solid stationary medium. Essentially, the key idea is that different components in a mixture will stick to the solid phase to varying degrees. To set this up, we pack adsorbents like silica gels, charcoal powder, or calcium hydroxyapatite into a glass tube, forming the stationary phase. Then, we load our sample mixture, dissolved in a solvent, onto this column. As the mixture flows through, each component interacts differently with the adsorbent. Some molecules will adhere more strongly, while others will pass through more quickly. This differential adsorption is what allows us to separate the mixture into its individual parts. Now, let's talk about the principle behind this process. It involves a competition between the components of the sample for active sites on the adsorbent surface. These active sites are typically formed at the molecule's cracks and edges, which are more reactive spots. The electrostatic forces within the molecules, which help hold the crystal lattice together, also play a role. They tend to extend outward and influence how molecules interact with the adsorbent. The separation occurs because of a dynamic equilibrium. Some molecules are adsorbed onto the stationary phase, while others remain in the mobile phase and flow along. The critical point is that the more a molecule has an affinity for the stationary phase, that is, the stronger its attraction, the less it will move with the mobile phase. So, molecules with higher affinity will take longer to pass through the column, allowing us to distinguish and isolate each component based on their adsorption properties. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about paper chromatography, an analytical technique that helps us separate and identify mixtures, especially those that are colored or can be made colored. It's a liquid partition chromatography method, meaning it involves a liquid phase separating components based on their different affinities. This technique is particularly useful for separating amino acids, sugars, sugar derivatives, and peptides. The stationary phase in paper chromatography is water held on a solid support, which is usually filter paper made of cellulose. Think of the paper as a medium that holds water in place, providing a surface for separation. The mobile phase, on the other hand, is a mixture of immiscible solvents. These are solvents that don't mix with water. Typically, it includes water, a nonpolar solvent, and sometimes an acid or base to help facilitate the separation process. When we talk about the mobile phase, it can be pure solvents, buffer solutions, or mixtures of different solvents, depending on what we want to separate. Now, mobile phases can be hydrophilic or hydrophobic. Hydrophilic mobile phases are water-loving, and examples include mixtures like isopropanol, ammonia, and water, or methanol and water in different ratios, such as 9, 1, 2, or 4, 1. N-butanol, glacial acetic acid, and water in a 4, 1, 5 ratio are also used. For hydrophobic mobile phases, which repel water, common examples are dimethyl ether with cyclohexane or kerosene combined with 70% isopropanol. These are chosen based on the polarity of the substances you're trying to separate. In summary, the choice of mobile phase, whether hydrophilic or hydrophobic, depends on the specific mixture you're working with, and it plays a crucial role in achieving effective separation. Now, different compounds in the sample mixture travel at different rates. This happens because of differences in how soluble they are in the solvent, and also because of how strongly they are attracted to the fibers in the paper. This is the core idea behind paper chromatography, separating mixtures based on these properties. The process can take anywhere from a few minutes to several hours, depending on the sample and conditions. It begins with applying a small spot of the sample onto a strip of chromatography paper, usually about 2 centimeters from the bottom. Next, we dip the paper into a suitable solvent, like ethanol or water, making sure that the sample spot is above the surface of the solvent. Then, we place the setup in a sealed container to prevent evaporation. Once the solvent starts moving up the paper by capillary action, it dissolves the sample mixture. As the solvent travels upward, it carries the different compounds with it, but at different speeds depending on their affinity for the solvent and the paper fibers. This is how the separation occurs, allowing us to analyze the components of the mixture effectively. Now, let's take a closer look at ascending and descending paper chromatography. In ascending chromatography, the setup is such that the solvent is placed at the bottom of the vessel. The paper is held upright, and the solvent begins to move upwards through the paper. This movement occurs because of capillary action, which is a process where the liquid rises against gravity due to surface tension and adhesion. It's quite fascinating because the solvent travels upward, carrying along different components of the mixture at different rates, helping us to separate them. On the other hand, in descending chromatography, the process is a bit different. Here, the solvent is placed in a trough at the top of the chamber. Instead of the solvent moving up, it flows downward through the paper. This flow happens not only because of capillary action, but also due to gravity pulling the liquid down. By understanding these two methods, we can choose the most effective technique depending on what we need to analyze or separate. Both methods are essential tools in chromatography, helping us to see how substances move through a medium under different conditions. Now, let's take a closer look at the analysis part of paper chromatography. After completing the experiment, the paper that remains is called the chromatogram. This paper shows us how the different components have been separated. The key idea here is that these components differ in their retention factor, or RF value. The RF value is essentially the ratio of the distance traveled by a particular component from the origin to the distance traveled by the solvent front. Think of it as a way to measure how far each substance moves relative to the solvent. If the RF value is 0, it means the substance didn't move at all and stayed in the stationary phase. That's what we call immobile. On the other hand, if the RF value is 1, it indicates that the substance traveled with the solvent front, showing it has no affinity for the stationary phase. It's important to remember that the RF value can never be greater than 1. That would imply the substance traveled farther than the solvent front, which isn't possible under normal conditions. Now, let's talk about detecting these substances. If the components are colored, they're easy to see directly on the paper. But if they're colorless, we need to use physical or chemical methods to visualize the spots. This is crucial because it allows us to identify and analyze the different components effectively, which ties back into understanding the composition of the mixture overall. When it comes to detecting and visualizing agents on a substance, the first thing to note is that if the substance is colored, it becomes quite easy to identify visually because the color itself acts as an indicator. However, the situation gets a bit more complex when dealing with colorless substances. In those cases, we need to rely on physical and chemical methods to detect the spots. Physical methods are generally nonspecific but useful. For example, the iodine chamber method is one such technique, which can help reveal certain compounds. Similarly, a UV chamber can be used to detect fluorescent compounds, either at 254 nanometers or at 365 nanometers. These methods are quite handy for quick screening. On the chemical side, we have more specific detection techniques, usually involving spraying reagents onto the substance. For instance, ferric chloride is used to identify phenolic compounds and tannins because they react to produce characteristic colors. Ninhydrin, applied in acetone, is excellent for detecting amino acids as it produces a purple or blue color when they are present. Then there's Dragendorf's reagent, which is used specifically for alkaloids. It produces a distinctive color change that indicates their presence. Lastly, for alkaloids and cardiac glycosides, 3,5-dinitrobenzoic acid is employed, which reacts with these compounds to give a specific visual response. These detection methods, both physical and chemical, are crucial tools in identifying substances accurately, which is fundamental in our overall analysis process. Let's talk about two-dimensional chromatography. This technique is especially useful when we're dealing with complex mixtures that don't get fully separated in just one run using a single solvent system. In other words, sometimes one round of chromatography isn't enough to resolve all the individual components clearly. So what do? We perform a second run, but this time with a different solvent system that's orthogonal or perpendicular to the first. This means we change the direction of separation, which helps to improve the overall resolution. By doing this, each component of the mixture gets a better chance to be separated from the others, making it easier to identify and analyze each one. This approach really enhances our ability to resolve complex samples, connecting to the overall theme of improving analytical precision in chromatography. Paper chromatography is a very simple and efficient method for separating different substances. It's quick, easy to perform, and can be used even when you only have microgram quantities of a sample. This makes it really versatile in various applications. You can use it to separate a wide range of materials, including amino acids, oligopeptides, sugars, oligosaccharides, glycosides, purines, and pyrimidines, as well as steroids, vitamins, and some alkaloids like penicillin, tetracycline, and streptomycin. However, it's important to note that paper chromatography isn't ideal for separating proteins. Proteins tend to be insoluble in many solvents used in this technique, and they can also get denatured during the process, which makes separation difficult. Lastly, while paper chromatography is useful, it's actually considered to be less powerful in resolving closely related compounds compared to thin layer chromatography. So, in terms of resolving power, thin layer chromatography generally provides better separation. Overall, paper chromatography remains a valuable technique because of its simplicity and applicability, but it does have some limitations depending on what you're trying to separate. For further support, please don't hesitate to reach out to us. We're here to help you with any questions or additional information you might need. Remember, your success is our priority, and we want to ensure you have all the resources necessary to move forward confidently. Thank you so much for your time and attention today. We truly appreciate your engagement and look forward to supporting you in your journey.